Have you ever noticed how, like, instinctively, we're always looking for the best way to do things? The quickest route, the most efficient way to finish a project, maybe the lowest price for something online. We're always optimizing. But what if we could use a kind of collective intelligence, something actually inspired by nature to find those best solutions? That's exactly what we're diving into today. It's this really fascinating computational method called particle swarm optimization. You'll often just hear it called PSO. And our mission here is pretty straightforward. We want to unpack how this works, look at how it mimics actual swarms like birds or fish, see where it's actually being used out in the real world, and understand the nuts and bolts that make it tick. Basically, give you a solid shortcut to getting up to speed on PSO.
Okay, so we're talking optimization, finding the best answer, and you said it's inspired by nature. How does that actually become a computational thing, particle swarm optimization?
It's pretty neat, isn't it?
Mm-hmm.
Yeah, so fundamentally, it's a computational tool for solving, tough optimization problems.
Mm-hmm.
But the real spark, the inspiration, it comes straight from watching birds flocking together or fish schooling. It's what we call a meta-heuristic algorithm.
Meta-heuristic. Okay.
Yeah, basically a fancy way of saying it's a general strategy, a framework you can adapt to lots of different problems. And it's all built on that natural swarm idea. The core concept is this. You have a group of particles. You can just think of them as potential answers, potential solutions. And these particles are moving around in what we call a solution space, basically the landscape of all possible answers, trying to find the best spot. Now, each particle adjusts how it moves based on two key things. First, its own experience, the best place it has personally found so far. We call that its personal best, or G-best. And second, the experience of the group, the best spot found by any particle in the whole swarm. That's the global best, or G-best.
Ah, okay. So it's like a team searching for something. Everyone remembers where they found something good, but they also pay attention when someone shouts, "Eureka! Found it over here."
Exactly. That's a great way to put it. Everyone learns individually, but they also learn from the collective success.
That clicks. It feels very distributed, very collaborative. Okay, so understanding the concept is one thing. But how does the swarm actually do it? How does it operate, step by step to find that best solution? What are the mechanics?
Right, let's get into the process. It starts with initialization. Basically, you just scatter a bunch of these particles randomly across the search space. Each one gets a random starting position and a random initial velocity, kind of giving it a random direction to start exploring. This makes sure you cover the area initially.
Okay, so they're just thrown out there to begin with.
Exactly. Then comes the evaluation part. Each particle looks at its current position and calculates how good it is, using something called the objective function. This function is just the mathematical way of defining what you're trying to optimize. Are you trying to minimize cost, maximize efficiency? That function tells the particle how well it's doing right now.
Makes sense. It needs a score.
Precisely.
Mm-hmm.
And after they get their score, they update. This is the key step. They adjust their velocity, how fast, and in what direction they're moving. And this adjustment considers, like we said, their own personal best position and that global best position found by the swarm.
So they're pulled towards their own past success and the group's success.
That's it. It's a balance. And this whole cycle, evaluate, update, move, it just repeats over and over. It's iterative. The particles keep moving, keep adjusting, learning from each other until, hopefully, they all start clustering around a really good solution, or until we tell them to stop after a certain number of tries.
That whole iterative thing, the collective learning, it sounds really effective. What makes this approach stand out? Why is it used so much?
Well, that iterative learning is exactly where the advantages come from. For one, it's actually surprisingly simple to code up and implement compared to some other complex optimization methods.
Really? Okay.
Yeah, the basic logic isn't super complicated. Second, it performs really well on problems that are nonlinear or complex, maybe have lots of dimensions, things where more traditional math-based methods might just get completely stuck or find a bad answer. Its ability to kind of explore broadly but also zero in on promising areas makes it quite robust, and that's why you see it popping up in, well, all sorts of fields.
Right, which brings us to the applications. Given how powerful it sounds, where is PSO actually making a difference, like in the real world? Got any surprising examples for us?
Oh, the applications are incredibly diverse. It's quite amazing. Take power engineering and renewable energy. It's not just theory. Think about hybrid systems like combining solar power, which varies with the sun, and maybe hydropower, which varies with water flow. PSO helps optimize their operation in real time. There's a specific example, the Mero Dam in, I believe, Zambia, where PSO helps manage the unpredictable river flow alongside solar input. It dynamically figures out the best way to generate power and keep the grid stable. That's tricky stuff to do manually.
Wow, okay, so managing the unmanageable almost, that's huge for renewables. What about, say, AI? That field moves so fast.
Absolutely vital in AI and machine learning. One big use is hyperparameter tuning. That's basically finding the best settings for an AI model before you train it so it learns effectively. It's a huge search problem.
Ah, tuning the knobs of the AI itself.
Exactly. PSO is great for that. It's also used for feature selection, figuring out which pieces of data are actually important for the AI to pay attention to, which improves performance. And sometimes in creating hybrid algorithms for classifying data more accurately.
Okay, so energy, AI, what else? Where else are these virtual swarms buzzing around?
Well, in communications and networking, think about your phone. PSO helps optimize how frequencies are allocated in wireless networks to avoid interference, so everyone gets better signal. It helps figure out the best routes for data packets in complex networks, making sure your internet traffic gets where it needs to go fast. It's even used in designing better antennas.
Okay, efficiency again. Makes sense.
And in robotics and control, it's used for path planning, figuring out the best route for a robot to take. It helps improve adaptive control systems, making machines respond more smoothly and accurately, and even figuring out the best place to put sensors in, say a distributed monitoring system.
I can definitely see the optimization angle there. What about less techy areas, finance, maybe even building things?
Definitely. In finance and economics, PSO is used for portfolio optimization, trying to get the best mix of investments to maximize return for a given level of risk. It also pops up in financial risk modeling and sometimes in building hybrid models for market prediction, though that's always tricky.
Sure, predicting markets, the holy grail.
Yeah, indeed.
Hmm.
And yes, in civil engineering and architecture, it's used to optimize the design of structures, like bridges or buildings, for strength and material usage. It helps plan resource allocation in big construction projects to minimize cost or time, and even optimizing energy use in smart buildings.
That's incredible. From digital networks to actual concrete. And did you mention medicine earlier?
I did, yeah. In medicine and biomedical fields, it's proving useful too. Things like improving the classification of medical images, helping doctors spot tumors or anomalies more accurately in scans. It assists in analyzing complex biosignals like ECG from the heart or EEG from the brain to find subtle patterns, and even in drug design, helping explore different molecular structures to find potentially effective new medicines. Yeah, the sheer range it's really something. It just highlights how this idea, borrowed from nature, can be incredibly powerful for solving really complex human-made problems, all the way from power grids to drug discovery.
Okay, so let's say you wanted to use PSO. You're setting it up for a problem. What are the actual dials you're turning, the parameters? Maybe we can use a simple example, like trying to find the lowest point in a smooth bowl. That's kind of what PSO does with something like the sphere function, right? It just sums the squares of the input, so the bottom, the minimum, is right at 0. How would the parameters work there?
Great question. That gets us under the hood, as you say. What are the knobs and dials we actually control? These are the core PSO parameters. First, there's num-particles. Pretty straightforward. How many searchers, how many potential solutions are in your swarm? More particles usually means better exploration, covering more ground.
Okay, the size of this search party.
Exactly. Then num dimensions. This is just how many variables you're trying to optimize. That sphere function, if it's just x and y, it's 2D. If it's more complex, it could be many dimensions.
Got it.
Then max iterations. How many rounds of that evaluate, update, move cycle do you let the swarm run for? More iterations means more time to potentially find a better solution, but it also takes longer.
Makes sense how long they get to search.
Now, the really interesting ones are the weights that control how they move. There's W, the inertia weight. This controls how much a particle tends to keep going in the same direction it was already going. It's a balance between exploring new areas, high inertia, and exploring known good areas, low inertia.
Okay, like momentum. Keep going or slow down and look around.
Precisely. Then you have C1, the cognitive weight. This is how much importance a particle gives to its own personal best position. A higher C1 means it's more strongly pulled back towards the best spot it found. It encourages individual learning.
Right, trust your own experience.
And finally, C2, the social weight. This is how much importance a particle gives to the swarm's global best position. A higher C2 means particles are more strongly pulled towards the best spot found by anyone in the group. It encourages collective learning.
So follow the leader, essentially. It's a balance between trusting yourself and trusting the group.
Exactly. Tune these parameters, WEC1, C2, along with the swarm size and iterations, is key to getting good performance out of PSO for a specific problem.
It would be amazing to actually see this happen. We can't show a live visual here, obviously, but maybe you could describe it. Like for that 2D sphere function example, how would the particles actually move towards the bottom of the bowl at 0, 0?
Yeah, visualizing it definitely helps solidify the idea. Okay, imagine a 2D plot, like a map. At the very start, iteration 0, you'd see maybe 30 or 50 blue dots. Those are our particles scattered completely randomly all over the map. No pattern, just spread out.
Okay, random starting points.
Right. Now, fast forward a bit, maybe halfway through the iterations. Let's say these are orange dots now. You'd see a clear trend. The dots wouldn't be randomly scattered anymore. They'd be noticeably closer together, and the whole cluster would be drifting, moving generally inwards towards the center, towards that 0, 0 point, which is the lowest point we're looking for.
So they're starting to cooperate and move together.
Exactly. They're influencing each other,
Yeah.
pulling towards the better solutions being found. Now, fast forward to the very end, the final iteration. Let's make these green dots. What you'd likely see is most, if not all, of the green dots clustered extremely tightly right around the origin, 0, 0, maybe marked with a big red X. They've converged. The swarm, through that process of sharing personal and global bests, has effectively navigated the space and honed in on the optimal solution.
That paints a really clear picture. You can almost see them swirling inwards. It shows how that simple social dynamic leads them right to the target. Okay, so PSO is clearly good at finding the bottom of a smooth bowl, like the sphere function. But what about trickier landscapes? You know, terrain with lots of hills and valleys, false bottoms, maybe narrow ridges. Are there tougher tests for PSO?
Oh, absolutely. That's a crucial point. How robust is PSO when the going gets tough? Researchers don't just test it on easy problems. They use a whole suite of what are called benchmark functions. Each one is specifically designed to pose a different kind of challenge, to really stress test the algorithm.
Like an obstacle course for optimization algorithms.
Exactly like that. For instance, there's the rastrogen function. It's famous or infamous for having a huge number of local minimal little dips that look like the best solution but aren't the real global minimum. It's a great test of whether an algorithm can avoid getting trapped in those suboptimal spots and find the true lowest point.
Okay, so it tests exploration, avoiding traps.
Right. Then you have something like the Rosenbrock function. Its challenge is different. It has this long, narrow, curved valley leading to the minimum. Algorithms can find the valley easily enough, but actually navigating down the curve efficiently without bouncing off the steep sides is really difficult. It tests convergence speed and precision in tricky geometries.
Ah, so navigating difficult terrain.
Another one is the Ackley function. It's got lots of small local minima, but superimposed on a large bowl-shaped structure. And the global minimum is this sharp dip right at the center. It tests robustness. Can the algorithm handle both the local bumps and the overall global trend?
Okay, multi-level complexity.
And one more, the Grewank function. This one is just complex. Highly multimodal, meaning tons and tons of local minima all over the place. It's a really rigorous test of an algorithm's ability to perform true global optimization, to sift through a massive number of possibilities.
Wow. So testing PSO against these functions shows it's not just for simple problems. It's actually designed and proven to handle some seriously complex, deceptive optimization landscapes.
That's the idea. It's a versatile tool precisely because it can tackle these kinds of challenging scenarios effectively.
Well, we've really covered a lot of ground today on particle swarm optimization. We've gone from its roots in nature, watching birds flock,
Yeah, the simple idea of swarms.
to unpacking the mechanics, how the particles actually move and learn.
The P-best and G-best.
And then exploring this huge range of applications from power grids and AI all the way to medicine and building design. It's pretty incredible.
It really is. And what strikes me is still the sort of elegant simplicity underneath it all. How this concept of collective intelligence, even simulated, can lead to such powerful solutions for really complicated real-world stuff.
So maybe a final thought for you, our listener. The next time you're facing a problem with seemingly endless options could be optimizing your schedule, planning a project, even just figuring out the best approach to a tricky conversation. Think about the swarm. What if you consciously tried to apply that principle? Combining your own best ideas, your personal best, with the best ideas and insights you can gather from others, the global best. How might that help you navigate towards your own optimal solution? Just something to think about.